We can gain a significant amount of insight simply by analyzing confidence intervals around our point estimates. Let's say we had a set of data for monthly revenue. A manager can use a confidence interval to estimate future months' revenues, or even estimate from a small sample the average sales for customers of a given type. So let's focus on how these confidence intervals are generated and how we can interpret them more effectively. Remember that any analysis of point estimates is how good is the estimate against the population parameter itself. If it's good, then we can understand something about the entire data set. If it's not good, then it's pretty much useless. Recall that the sample should give a reliable estimate if it is a good sample, but we are going to be somewhat off. Therefore, we want to create a confidence interval, or an upper bound, lower bound, by which we have a high degree of confidence or certainty where the population parameter lies. So on the graph here, we have a point estimate in the middle, and our upper bound will be some value above, and our lower bound will be some value below. So our confidence interval will always have the form of the point estimate, plus or minus, some multiple, which is going to give us our confidence level, times the standard error, which is the standard error against the point estimate. So we need to know how to calculate this point estimate, obtain our multiple from a given distribution, and then calculate the standard error. So let's take a look at creating z-values from our sample distribution. So from a previous module, we saw that the normal distribution is very appealing and useful. When we have a sampling distribution that is approximately normal, we can create a standardized value using the formula below. On the graph on the right, we see that this is a standard normal distribution with a mean of 0 and a standard deviation of 1. Now, the z-score we will calculate is going to change a little bit from what we had originally done, because now remember that when we're using the sampling distribution, the standard deviation is going to slightly change according to the central limit theorem. So as n becomes larger, the distribution will tend to normal with a mean of mu and a standard deviation of sigma divided by the square root of n. So our z-score calculation changes a little bit, and it becomes z equals x bar minus mu in the numerator over sigma, which is the standard deviation, divided by the square root of n. The population standard deviation, which is sigma, is never truly known, and we call this a nuisance parameter. So in order to compensate for this, we're going to substitute sigma with the sample standard deviation. But once we do this, this introduces another set of variation that we have to account for. In order to account for it, we're going to have a slightly different distribution called a t-distribution. So this t-distribution is very similar to the normal distribution, but it is used to estimate the z-score from a distribution with the added variability mentioned from the previous slide. So the graph on the right shows the t-distribution. The difference in the curve occurs in something called the degrees of freedom. The degrees of freedom is always equivalent to 1 minus the total number of observations. So if we had 30 observations, we would have 29 degrees of freedom. If we have 100 observations, we would have 99 degrees of freedom. Now, that is for the t-distribution. Other distributions will have different degrees of freedom, but we'll discuss those later. The red line has a degree of freedom of 5. Now you're going to see in this chart here on the right that it looks normal, but it's slightly different. In fact, the dashed line put here is actually the normal distribution, a standard normal distribution. So when the degrees of freedom is 5, the actual curve, the top of the center curve, is a little bit down, and the tails are slightly up. But as we increase the number of observations, our degrees of freedom will also increase. And we see that the blue line is at 30 degrees of freedom, and the green line is at 100 degrees of freedom. And you can see that it tends closer and closer to the normal distribution. So now what we're going to do is remember that we were looking to standardize the z-value through the formula shown here. But because we don't know the standard deviation of the population, we're going to replace it with s and introduce variability. So our standardized value now becomes what we call a t-value using the t-distribution. And this becomes t equals x bar minus mu over the sample standard deviation divided by the square root of n. And we can now interpret the t-value that we get as the number of standard errors the sample mean differs from the population mean. A closer look at the formula reveals that the numerator is the difference between the sample mean and the population mean, and we divide that by the estimated standard deviation of the sample distribution, which is divided by the square root of n. So the formulas are very similar. The only difference is that we have now replaced the population standard deviation with the sample standard deviation, and we're obtaining a similar score, but the top one, which is the population standard deviation, would be the z-score, and the bottom one is from a sample standard deviation, which is now known as a t-score. So in Excel, we're going to use the t.dist functions to calculate the area under the curve from that given point. So recall from the modules on probability distributions, we could, using the distribution formulas in Excel, we could calculate the area under the curve to the left. So if we have a sample of 25 scores, our degrees of freedom would be 24 and minus 1. So t.dist, 0 being the x value, comma 24 degrees of freedom, would give us a result of 0.5. And that means that 50% of the curve lies to the left of 0. If we did t.dist 1, comma 24, it would give us a result of 0.83, which means that 83% of the curve lies to the left of 1. And 1 minus t.dist 1.5, comma 24 would give us 0.073. So that means, again, when we do the 1 minus, the t.dist 1.524 gives us everything to the left. Doing 1 minus would give us everything to the right. Now, we have another function in Excel for the two tails. So we want to know the area under both tails, on the left and the right. So what will happen is that when we do t.dist.2t for two tail, 2.0, comma 24, this will give us 0.056, and it will provide the area under both tails, the left and the right, at both 2 and negative 2. So each tail will have 1/2 of that value, and that would be 0.025. We could also do the reverse and say, let us have the x value, or the t value, where the probability of the curve is 95%. So if the area under the curve is 95%, consider it would be most of the curve from the left side past the middle point all the way to about 95%. And it will give us a t-value of 1.71. That's where 95% of the curve is to the left of 1.71. We can also do the reverse and say, give us the area, provide the t-value where 95% is between the two tails. So for example, we will do t.inv.2t 0.95 is 2.06, and the result is 2.06. So the 95% is between the two tails. That is that 5% of the area is under both tails, 1/2 on one side and 1/2 on the other side, or 0.025.